In this video, I'll be explaining how to find the characteristic function of a normal random variable and a Poisson random variable. So let's take a look at the normal random variable first. The PDF of a normal random variable can be given by this formula right here, which we all know. Now the characteristic function definition is given by this formula, which is an integral from minus infinity to plus infinity e power j omega x probability density function if the random variable is continuous, which in our case is normal random variable which is continuous. So now let's substitute this fx of x in this equation. So what we get can be seen in this equation right here. Now this looks very complicated. To simplify it, let's substitute x minus mu as y. So what we can do in this equation is we can substitute x as y plus mu and x minus mu as y. So the result can be seen in this equation right here. Now this still looks complicated, so to simplify it further, we can take 1 e power j omega mu term outside. We can see the result right here, and then we can merge these two exponential terms together. So once we do that, what we get can be seen here. And then to simplify it further, we can take 1 y outside and then do another substitution for y minus j omega sigma square as u. So what we get after this substitution in the earlier equation is this equation right here. Now these two terms can be simplified as u square minus j omega sigma square whole square, which the resultant can be seen in this equation, which forms e power minus u square by 2 sigma square and e power minus omega square sigma square by 2. Now this minus term came because of the squaring of this j term in the last step. So if we look at that equation closely enough, we can see this is nothing but an integral from minus infinity to plus infinity, the probability density function of a normal random variable u. So which we all know is nothing but 1. So what we are left with is e power minus omega square sigma square by 2 and e power j omega mu omega. So these two terms can be merged together to get the characteristic function of a normal random variable. Next, let's take a look at a Poisson random variable x. So the probability density function of a Poisson random variable x can be given by this equation right here, which is nothing but e power minus lambda power k by k factorial. Now since this is a discrete random variable, the formula for the characteristic function will be slightly different. In the last case we saw an integral here, but in this case we'll be having a summation for k is equal to 0 to infinity. So after substituting this PDF in the characteristic function, what we get can be seen in this equation. So this term is e power j omega k, which we have to insert, and this term is nothing but fx of x of a Poisson random variable, which is this. So to simplify it further, let's take lambda e power j omega together from these two terms and take e power minus lambda outside. So but we know that summation of a power k by k factorial over k is equal to 0 to infinity is nothing but e power a. So by using this property in this equation, what we get can be seen here. which is nothing but e power minus lambda, e power lambda, e power j omega. Now after merging these two exponential terms together, what we get is this equation, which is e power lambda, e power j omega minus 1, which is the characteristic function for a Poisson random variable.